Covalent molecules. Covalent molecules share electrons as opposed to ionic bonds, which we've looked at before, metallic bonds. We're going to look at what covalent molecules are today. So you should have your note sheet with you. These are the 6 main topics we're going to cover. What is covalent bonding, the properties, how to name them using the prefixes, the rules for the naming, how to write the formulas, and what are diatomic molecules. So by the time you are done, each one of these should be something you could talk about. So you'll notice there are 3 main types of chemical bonding. We've already talked about ionic bonding. We said that is an electrostatic attraction between a cation, which is a metal, and an anion, which is a nonmetal. So the cations are going to give away the electrons to the nonmetals, which are going to receive those valence electrons, and they form this magnetic attraction. Acids, which we'll see in a little bit on another video, are also ionic bonding, but they start with an H. Metallic bonding, we don't talk too much about naming them because you just name the metal as is, or it's an alloy, which is a mixture of metals. But metallic bonding are cations, which you see here. And these cations are going to be in a sea of valence electrons. So the cations all donate their valence electrons to the kind of the general area around all the cations. And then those sea of electrons kind of form like this kind of shield or this area of protection. So it allows the cations to move next to each other without repelling. And that's why ionic bonds, for example, if you have like a salt lamp and you drop it on the ground, it's brittle, it's hard, it's going to shatter, as opposed to something that is like a metal. And if you dropped a metal bowl or a metal lamp on the ground, it would just dent. Covalent is a whole nother category. Now our electrons aren't being donated to a sea of electrons and they're not being given and taken. They're actually going to be shared between a nonmetal and a nonmetal. So there are no ions in covalent bonding, so that means we won't have any polyatomics also. So nonmetal plus a nonmetal or multiple nonmetals will make a covalent bond and they'll be sharing those electrons. So a little bit more looking at covalent bonding. So it's a chemical bond that is a force. So remember, a chemical bond is a force that holds 2 things together. Again, we've looked at ionic and metallic, but we're going to focus on metallic now. So atoms form a bond to become more stable. And when we say stable, we say they obtain an octet. So here you can see that in covalent bonding is between a nonmetal and nonmetal or a metalloid and nonmetal. For our purposes, we're going to mainly focus on all nonmetals. And an ionic bond is a metal and a nonmetal. Remember, the metals are to the right of the staircase. Here, we have 2 fluorines, and they both need 1 more electron. So they're going to join together and share both of their 7th electrons to make the other's 8th electron. So now this fluorine has access to 8, and this fluorine has access to 8. Same with water. Hydrogen, which only needs a duet, needs 1 more. This hydrogen needs 1 more too. So if it bonds with oxygen, it can share these 2 electrons, and that will give oxygen the 2 that it's missing. So as you can see down here with chlorine, and we're going to say anything that bonds to itself and forms a diatomic molecule that is like chlorine. It always is going to be found in nature and bonded to itself. We'll learn more about that at the end of the video. But you can see chlorine, they're both unstable. They both need just 1 more electron. So if they join together and share their forces and put all the resources together, then they both can fulfill their octet, which makes them stable. And the whole reason all of these atoms want an octet is because it takes less energy for that atom to stay together. And you'll see everything in nature wants to spend the least amount of energy, like spending the least amount of money. And so these electrons are going to be shared between 2 or more elements. It's always between 2 nonmetals. And don't forget that a metalloid can act as a nonmetal. And those metalloids are typically boron. So you might want to write these down in your notes. They're also found on our periodic tables as we've labeled them. And we'll look at them some more in class. Silicon, Si, germanium, which is Ge, arsenic, which is As, and antimony, which is Sb. Metalloids can act as nonmetals, and you will never have a polyatomic in there. Again, remember, polyatomics are covalently bonded atoms with an overall charge. So we see polyatomic ions within an ionic bond, acting as either the metal or nonmetal. So the bonding results from a mutual attraction of the two nuclei. Nuclei is just that nucleus in the center. It's the plural form of nucleus. And they're going to share their valence electrons. And not all electrons are shared in a covalent molecule. So notice here that the only ones being shared are the ones that are highlighted in that pink or red color. The green ones, we would call these lone pairs. They're being shared on their own, or they're not being shared. They're unbonded. So we would call the pink or the red ones bonded electrons. So that's where a bond is. So between a chlorine atom and another chlorine atom, there is one bond. And that bond is a single bond because there's only one of them. And then the green ones that you see there, all of those are going to be what we call a lone pair or unshared electrons. So they're over here and they have a lot of repulsion power. So that's something to note about them. All right, we're just going to take a look at a few more examples between an ionic bond and how to kind of compare it to covalent. So you'll notice that ionic, again, had that electrostatic attraction. It had ions. Lithium lost an electron, so it became more positive. Fluorine gained an electron, and it became more negative. As opposed to bromine or carbon and oxygen, all of these are nonmetals. So you have two nonmetals bonding. They're going to share electrons. We represent shared electrons by a line. And we won't be doing too many drawings this year. It's going to be an abbreviated version. But if you're watching this in a future year past fall 2020, we may be drawing them. So you can see carbon bonded to an oxygen has a triple bond. The strongest bond is going to be a triple bond. It's also the shortest bond. The longest and weakest would be a single bond. So again, you can kind of see the differences. So we see that metal and nonmetal forming the electrostatic attraction, giving and taking of electrons. Covalent, they are sharing between two nonmetals and forming a bond. An example of covalent is water. Example of ionic would be a salt. Notice that water can act polar and have a positive and a negative side. And if we were drawing this out, if you look here in the oxygen, oxygen has 1, 2, there's a pair, so that's called a lone pair. 3, 4, there's another pair. So it has two lone pairs. And so those two lone pairs are actually on this side, and that's what's creating that negative end. And so the electrons are actually going to hang out towards oxygen. If you take a look on your periodic table, you notice oxygen is right next to fluorine, and fluorine is our most electronegative element. So that is why those electrons are hanging out closer to oxygen than hydrogen. So how is that covalent bonding different than the ionic bond? So we just kind of talked about that a little bit on the last slide, but now kind of pause the video, take a look at the items on the screen, and write about 3 sentences of the difference between covalent and ionic. Tell me, are the electrons being given or taken? Are they being shared? What's being bonded? A metal and a nonmetal, or all nonmetals? Are electrons transferred or shared? Do they have high melting points or low melting points? You'll notice that, remember, ionic has high, covalent has low. Ionic compounds are usually hard and brittle, and covalent are usually relatively soft. Ionics are soluble in water, and covalents are insoluble, meaning they don't dissolve in water. Now you're like, well, doesn't water dissolve in water? Well, technically it has to be able to pull it apart to make ions. That's what dissolving means. So no, it's not dissociating or dissolving. Although sugar, you can put in water, it just gets smaller and smaller. It doesn't pull it apart. So there's difference between dissociation and dissolving. And when we're talking about soluble, we mean dissociation. So when you put salt in water, this polar molecule is going to pull on that positive sodium, and then the positive end is going to pull on the chlorine and pull it apart so that you have ions floating in the water. And when those ions are floating in the water, then you can conduct electricity through it because you have electrons or negative ions, the anions, freely floating. Remember, you can pause this video at any time. You can rewind and re-listen to it to make sure that you caught everything I said in case I said something that was not on the screen. And actually, I just noticed something that's weird in this chart is that covalent compounds are the ones that are named with the Greek prefixes. The ionic compounds uses the Roman numeral. So Let's see if this will let me write on it. This is actually covalent. And then, of course, we've already learned this, Roman numeral goes with ionic. So that is wrong on that chart. That's a bummer. Can't count on that internet all the time. All right, let's take a look. Hopefully you took time to pause and write your 3 sentences. Properties of covalent molecules. So they're poor conductors. They have low melting points and boiling points, or at least lower than ionic, because covalent bonds are usually weaker than the ionic bonds. So again, stronger the bond, the higher the melting point, the more energy it takes to break those particles apart. Covalent does not take as much energy to break apart. So think about salt is ionic. It takes a lot of energy to melt salt, as opposed to if you put sugar on the stove, it melts pretty fast. Covalent molecules are usually liquid and gases. They're more flammable than ionic compounds, and they are insoluble or they don't dissolve well in water, meaning that water can't pull them apart. So here are some things that can conduct electricity. Notice that silver, gold, copper, and steel all have metals in them. And then seawater has salt dissolved in it, and so that's why the water is able to conduct electricity. If you had just plain pure water, it won't actually conduct much electricity, contrary to popular belief. But when you have water like in a bathtub, you have a lot of ions in there. You have a lot of different metals. You've got chlorine, you've got fluorine, you have like iron and different things that have recycled from the pipes into your water. So when you are drinking tap water or have water in your bathtub, it's not pure. It's got a lot of ions in it, so that's why it conducts electricity. Rubber, carbon dioxide, oil, diamond is all made up of carbon, which is non-metal, and dry wood is mostly made up of organic material like carbon and oxygen. And so these would not be good conductors. So if you notice, insulators tend to be covalent, and things that conduct are either metals or salts that are dissolved in water. These are important prefixes that you need to memorize. So go ahead and pause the video and record these. Hopefully you had a chance to record these. Mono is 1. Usually I have you memorize these, but you could also write them on your periodic table. Di, kind of like di means 2. Tri, like tricycle. Tetra, 4. Penta, 5. Hexa, hepta, octa. There's also nona and deca, just for those of you that were wondering. So rules for naming a molecule. The first step is very similar to ionic, but now we're going to be adding prefixes. So the first element in the formula always just gets to be named first, and it gets the full element name. The second, you name the second anion. So we're usually going to be naming covalent molecules that only are binary, that have 2 in them, 2 elements. Then you're going to add the prefix to denote the subscript. Remember that subscript is that small little number where you have your, like, this would be my element, and then down at the bottom, you would have the, this side, you would have the subscript, and that would tell you how many. So like H2O means that you have hydrogen with that little 2, you have 2 hydrogens, and then you have oxygen, imaginary 1, and so that would be 1 oxygen. And that's why when you're naming oxygen, you say dihydrogen monoxide. Mono meaning 1, oxygen, and you end it in ide, dihydrogen monoxide. The prefix mono is never used for the first element, so that's why CO is called carbon monoxide, because we don't use mono for the first element. So just like how we don't typically write 1 in chemistry, so like again, when I said when you had H2O, this little 2 is a subscript. It tells you have 2 hydrogens, and then there's an imaginary 1 here to tell you that you have 1 oxygen. So we don't write mono for carbon monoxide. CO means you have 1 carbon, 1 oxygen. And so the formula is going to look like this. I have some stuff about to come up on the screen, but I think I'm going to have to go back. Oh, nope, it stays. Let's see if I can erase it. There we go. Okay, so we have CO2. This is carbon dioxide, but how do you know to name it? Name the first element, carbon. Name the second element, drop the ending, and add "ide." So carbon, oxide, and then you add your prefixes. and you get carbon dioxide. Notice that we didn't use mono, even though there's one carbon, because it was written first. Let's take a look at another one. So for example, we have BF3. So in this case, boron that can act as a metalloid, meaning semi-metal, metal, or non-metal, is acting as a non-metal. So from here on out, we're going to consider boron to be a non-metal. You won't see it in an ionic compound. So boron is F3, meaning we have one boron and we have 3 fluorines mixed with it. So how would we name this? Let's name the first element, which is boron. Name the second one, which is fluorine. Drop the last syllable and add "ide." Just like we did when we were naming ionic compounds and you were naming the anion, we would say fluoride, sulfide, nitride, oxide. So notice that ending here, that IDE. Then you want to add your prefixes. We don't use one because it's the first one, but we do have 3 fluorines, so it's going to be boron trifluoride. A lot of students find covalent a lot easier and as opposed to ionic naming. So pause the video and try some on your own, and then you can come back and check your answers. Okay, so let's practice naming. Hopefully you paused the video and gave it your best try. Notice that these are some common molecules to know. I believe ammonia is already written on your polyatomic ion sheet, but you can also add methane. Methane is the gas that we have in the chemistry room. It's that one that kind of smells like eggs, and they actually add that into the methane so you can tell if there's a gas leak. NH4 is ammonium. We've seen that polyatomic. That's on your polyatomic ion sheet, so make sure you don't confuse these two. That happens often. All right, so let's take a look. So number 1 says that we have N and O. And if you remember, we said we're going to name the first element, name the second element, but add IDE, and then we're going to go in and add the prefixes. All right, so this would be nitrogen, and then this would be oxide. I got oxide because oxygen turns into oxide. So now we have the prefixes. There's an imaginary 1 here, so there's 1 nitrogen, but we don't write mono for the first element. And then the second one also has 1, but we do write it, MON. Notice that it already has an O. I didn't put double O's there, so nitrogen monoxide. Number 2, we're looking at nitrogen and oxygen again, but this time we have 2 nitrogen and 5 oxygen. So we're going to name the first element just as it is on the periodic table. Name the second one, drop the last syllable, and add "ide," so we get oxide. 2, we're going to use the prefix of di, so dinitrogen means 2 nitrogen. 5 is going to be penta, P-E-N-T. Where did the A go? So 5 equals penta, but when it's next to a vowel like oxide, we don't write that A, so it's understood. Number 3. We have carbon and oxygen. So we name the first element, carbon. Name the second element, oxide. Imaginary 1, we don't put the mono. 2 means di, so we put dioxide. That's okay to have 2 vowels there. So carbon dioxide. Next, we have number 4, SiO3. This is going to be silicon trioxide. So oxygen, drop the last syllable, "ide." This 3 tells me I have 3 oxygens. Imaginary 1 says I have 1 silicon, but we don't write mono for the first one. Number 5 says carbon, and then it has 4 chlorines. So we have 1 carbon, 4 chlorines. So we're going to name the first element, carbon. Name the second element, drop the last syllable, and add IDE. So chlorine becomes chloride. 4 is tetra. So it's carbon tetrachloride. And so it should be carbon, there's a space there, and then tetrachloride. Next, we have number 6, which is F5. These are both nonmetals. That's how I would know it is ionic. They're all on the right side of that periodic table. I'm going to name the first metal, or the first nonmetal, iodide or iodine. I'm getting tongue twisted on this one. Iodine is the element. This one is fluoride, and it comes from fluorine. So fluoride. Penta means 5, P-E-N-T-A. Iodide, iodine, pentafluoride. I really want that to be iodide, apparently. But iodine, so just like the element, then penta, that's the 5, fluoride. Imaginary 1, but we don't write the mono. All right, 2 more examples. We have phosphorus and chlorine. We're going to name the first element, phosphorus. Name the second element, drop the last syllable, add I-D-E. So we change the I-N-E to I-D-E. 5 is penta. We're going to have pentachloride. Again, there's a space just in case it's not clear on how I'm writing it. So phosphorus, pentachloride. Last one. This time we have 4 phosphorus and we have 6 hydrogen. This is number 8. So we're going to name the first element, phosphorus. Name the second element, which is hydrogen. Drop the last syllable and you get hydride. 4 is tetra. 6 is hexa. So I'm just going to go back real fast to our prefixes. You can also look on your paper. Notice that hexa and hepta, sometimes people will mix those up. So you want to make sure that you're paying attention that hexa is 6 and hepta is 7. If you also think about it, hexa has 4 letters and hepta has 5. 4 is even and shorter and smaller than 5, which is odd, and 7. So now we just have to add our last prefix. So again, 6 is hexa. So we get tetra, phosphorus, hexahydride. So if we were going the opposite way and going from the word to the formula, and remember a formula, and I don't think I've said this in this video yet, is called a molecule. So remember how we had a formula unit was called an ionic compound, a covalent compound is called a molecule. So we would say phosphorus, tetra is 5, hexa means 6. Sorry, tetra means 4, hexa means 6, and we're looking at hydride, which is hydrogen. So you get P4H6. All right, so let's take a look at some more examples. Some things to remember, we're going to use these prefixes as the subscripts. We will not crisscross and we will not simplify. So these are a lot easier than ionic because there's a lot of less things that you have to do. So do not crisscross the subscripts and do not simplify. So let's take a look at these examples. So 1 says carbon monoxide. Carbon is C, oxide is oxygen. There's nothing written in front of the carbon, so that means imaginary 1. And mono also means 1. So mono equals 1, so we don't write anything. So the first one is CO, carbon monoxide. Number 2, carbon tetrafluoride. So we have a carbon. It doesn't have a mono. It's understood as 1. And then it says fluoride, which is F, or fluorine. Tetra means 4. So carbon tetrafluoride. Aren't these much easier than ionic? Dihydrogen, so N2, trioxide. Oxygen, 3. Dinitrogen, trioxide. Notice that these go together and these go together. It's just simply what it is. Number 4, selenium, Se. There's no mono in front of selenium, so we're going to assume it's a 1. Dioxide means 2, and oxygen. So selenium dioxide. It would be fun if you went and looked up some of these things. They have some interesting applications. And then the last one is just nitrogen monoxide, NO, because that mono is silent and that other mono means 1. All right. Finally, we're going to look at diatomic molecules. So you'll see that diatomic molecules exist naturally in pairs. They are 2 covalently bonded identical nonmetals, and there's 7 that you need to memorize. These 7 are naturally occurring in the atmosphere. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. So pause the video and fill in this chart here. Notice that this little 2 here means it has 2 hydrogen atoms. This 2 means 2 nitrogen atoms. That 2 means 2 oxygen atoms. And if you wanted to name it, instead of saying dihydrogen, you say hydrogen gas. Instead of saying dinitrogen, you say nitrogen gas. So it's oxygen gas, fluorine gas, chlorine, bromine, iodide. There are 7. Fun fact is on the periodic table, they actually form a 7. So see how this purple here is making a 7? And there's 7 of them, but don't forget to include hydrogen over here. So they make a 7 on the periodic table, and there are 7 diatomic elements. See how that's a 7? So, plus hydrogen. So you have all of these. There's a couple other ways people like to remember them. You can remember the name Brinkelhoff or H. Brinkloff. I've seen people memorize them in many different ways. Those are the 3 most popular. All right, that's covalent molecules. Please let me know if you have any questions in class, and have a great day.